Hey, what's going on YouTube? Welcome to the next tutorial in our series building a render engine. Today we're going to talk about matrices, but first I'm going to implement something that I should have done at first in the vector class. That is going to be a function called lerp, and what this will do is it'll basically linearly interpolate between two vectors based on a floating point value t. So if it's 0.5, it'll be right between the two vectors. If it's 0, it'll be at the first vector, and if it's 1, it'll be at the second vector. So the math here is the definition is A, const vector2 reference B, float t, make sure you have that, and then vector2 reference dest, because it's going to return a vector2. And let's copy this. Okay, and the math here is going to be a dot x plus b dot x minus a dot x multiplied by t. And we switch this with y in all these locations. And that is the lerping function. And one other thing I'd like to modify about the vectors is I'd actually want to delete these. And the reason for that is because we don't actually need them anymore if we make these public. I'd prefer to have the x and y variables public because it just makes it a little bit easier to use the vectors, and I don't want to type get every single time. Also, it makes it a little bit faster, so that's worth it in my book. And I've actually already taken the liberty of making all those changes to the vector3 class. There's really no difference except I added a z-axis, and once again I made these variables public. And I did the same for the vector4 class, adding this lerp function as well. And just be sure that it's b.x minus a.x, etc. And those will be the changes to the vector class. Let's make sure it compiles, and it does. Good to go. Alright, so let's get right into the matrices now. To start, let's make our files. We're going to be making matrix 22. I'm really bad at typing the word matrix for some reason. I keep typing it matrixi instead of ix. But yeah, we're going to be making 2x2 matrices, 3x3 matrices, and 4x4 matrices. Let's also make the source files. Now the way you can actually think of matrices is like, it's sort of like you have columns and rows. And those columns and rows represent certain axes. Well, specifically the rows, or the columns. In those columns you write vectors that represent the axes of a three-dimensional space. And using those axes, you can actually multiply vectors into the space of the matrix from a different space, and it actually translates the coordinates, assuming it's base Euler coordinates with a identity matrix. It actually translates it directly into the space of the new matrix. And what that's useful for is you can actually take all the points and then multiply it by, like all the points of a model, multiply it by that matrix, and then all the points are moved into the space. So you can scale things down, you can expand things, you can rotate things, skew things. It's a very, very useful system to represent the rotations of, or transformations of objects. And you'll see exactly what I mean when we start working on that. So let's go ahead and start with the matrix 22 class. Alright, so first I'm going to start by actually copying over the definition file, and I do think it's a good idea to do some copy and pasting this video, because it's going to be quite a tricky process. Well, it's not a tricky process, it's just a lot of stuff to type, and I'm not going to do this every tutorial. In fact, it's probably just going to be the math tutorials that we're working on. And the reason for that is, again, just because there's just a lot of stuff to type, and it's also pretty easy to mess up if you don't know what you're doing. This is our matrix 22 definition. I have forward declared vector 2 because we're going to be able to multiply vector 2's by this matrix. And I'm going to move this down to the next row, so that way you can visualize it as columns and rows. This is your one diagonal, and this is your other diagonal, and this is your first matrix vector, and this is your second matrix vector. So this will make up the x-axis of the vector space, and this will make up the y-axis of the vector space. And we're just making a constructor, a copy constructor, assignment operator, destructor, and then add's going to be exactly what you think it's going to be. You take the left and add it to the right. Same with sub. But mol's a little bit different here. What you do is you basically take the dot product of the columns and rows and set that to the values in the destination. I would recommend you look up a tutorial on how matrix multiplication works if you're interested. In the transformation, and I'll actually have a link to all the math in the tutorial in the description as well, so be sure to check those for reference. Here's the transformation. What this is going to do is effectively multiply a vector by the matrix, and matrix multiplication is non-commutative. So it's important that the vector 2 actually comes after the matrix 22, because if you put the vector 2 before, you actually cannot multiply the matrices together. So that's just a little bit of trivia for you. And also another thing to watch out for while we are building this, because if you don't multiply the matrices in the order that I do, it's going to be a problem. Store it into a destination vector. Next you have something called set identity. And this is going to be the matrix version of 0, or 1, sorry, excuse me. 1 is going to be, it has the property such that when you multiply it by any other matrix, it actually returns the original matrix. So if you have a matrix with A, B, C, D, and then you multiply it by the identity matrix, it will return a new matrix A, B, C, D. And that would go for every situation. 0 has the property you multiply any matrix by, it always has 0. Self-explanatory. Transpose, that's when you swap the elements across the identity diagonal. And I probably should have told you the identity diagonal, but that would be where you have this set to 1, this set to 0, that set to 0, and this set to 1. And what you'll notice is actually that falls in line with my definition of what a vector space is, because if this is 1 and this is 0, that's just 1 on the x-axis and 1 on the y-axis. So that's a perfect 2x2 coordinate grid, or a two-dimensional coordinate grid. And when you multiply any values from any other vector space into that one, you're just not making any change to the vector space, so it makes sense that there would be no change to the values. But transpose just reverses across this diagonal. The inverse function is going to have the property, it's very difficult to explain the math here, but you take the determinant and then it has the property such that if you take a matrix A and then you multiply it by A inverse, you actually end up with the identity matrix. That's a very, very useful one because it allows you to undo the transformations that have taken place in a matrix. So if you multiply vector A by a matrix A, and then you multiply that vector A by the inverse matrix A, you end up with the original vector. That's extremely useful, for sure. Negate, you just multiply each vector or each value by -1, and then the determinant is a constant function to get the values. So yeah, let's go ahead and start implementing this. First, let's include matrix 22.h and include vector 2.h. And then also, I'm going to start by copying and pasting the definitions here. Alright, so let's go ahead and paste that in here. So we got, in our main constructor, we're setting it to identity initially with an initialization list. This is set to 1, that's set to 1. This is set to 0, and that would be set to 0 as well. Now let's go ahead and well, actually, the copy constructor and the operator equals are both self-explanatory. We don't have to worry about any pointers, so it just makes it super easy. Now let's implement add and sub. I'm going to go ahead and copy this once again, save a bit of time. So it's very self-explanatory here. We just take the left and we add, and then we take the right and we add them together. The next thing we want to do is multiplication, and this is just an implementation of the dot product of every column and row, as I talked about before. And that's what this math is doing here. It's just taking the dot product. So if you remember, it was one value times another plus another value times the other. And that would be the matrix multiplication. Well, now let's do the transformation. This is multiplying it by a vector 2. The math is very similar to the normal mul function, just like that. And now we want to do set identity. So void matrix. So we want to do set identity. And this is going to be real simple. So m00 equals 1, m11 equals 1, and m01 equals 0, and m10 equals 0. That's the identity. And now let's do the same thing with set 0. Oops. Yeah, so set 0, now we'll just change those to 0. Now let's do the transpose, and remember that just flips across the axes. I'm going to copy this one because, not that I'm going to mess it up, just to save a small amount of time. So we're saving the temporary value and then setting this to that, and it's essentially just swapping the values. Real simple. Now we are going to do invert. This is the first, well, for most other matrices this is a pretty complicated function, but luckily for vector 2's it's not too complicated. That's what invert does. And now we will do negate. So that's going to be, well, I'll copy over negate and invert. I'm going to try to make this video less than 30 minutes if I can, otherwise that's alright. So that is the determinant function, just the definition of a determinant implemented for a 2x2 matrix. And negation as well, just real simple stuff. So that's the matrix 22 stuff. If we make, alright, I made an error. Oh, that wasn't, yeah, that was a miscopy, I think. Okay, that would be fixed now, so we will do so the matrix 33 is going to be very, very similar to the other one. I'm going to start by copying over the definition. So we got that, paste it in. This time I'm forward declaring the vector 3. And then we again have all the same stuff at the top. We have the virtual destructor. I'm not too concerned about memory, so it's fine to make it virtual. The only difference between these two and the last one is now we have more values. So this is going to represent the x-axis, this is going to represent the y-axis, and this is going to represent the z-axis. So once again, the identity matrix is going to be x0, or x1, y0, z0, y0, x0 for this one, y1 for this one, and z0, and then x0, y0, and z's to 0 for that. And that would be the definition of the matrix. Let's first copy over our operator equals and matrix stuff. I'm going to include matrix that and include vector3.h and then paste this in. So we're setting it to the identity once again in the constructor. And we also have our operator equals setting this here, and our copy constructor there, and our virtual destructor is implemented as well. And you don't actually have to, I should have said this at first, but in case you're not doing it already, I don't recommend actually following along by typing out this code. I'd recommend copying it and pasting it from the GitHub, just like I'm doing. The next functions we want to do are add and subtract. So those go in. Same exact thing as the vector 2, but we're doing it with more m0s and m1s. And that would be adding and subtracting. The next thing we're going to do is multiplication in transform. And this is the same thing as the vector 2, just with a vector 3, or a matrix 22, this time with a matrix 3. And you can see how it's taking the dot product of every element area and setting it into the destination. And then transform, same exact thing as the other one as well. Now we will do set identity. And the values that are going to be 1 for this one is m00 equals 1, m11 equals 1, and m22 is equal to 1. So m01 is equal to 0, and m02 equals 0, and m10 equals 0. M10 equals 0, M11 equals 0, and M12 equals 0, and then also M20 equals 0, M21 equals 0. So there's identity for the 3x3 matrix. Now let's go ahead and set 0. Oops. So we'll paste that in, change this to set 0. And then I will simply come down here and change those to 0. Now let's go ahead and do the transpose function, which I will copy and paste, because it's just a lot of stuff to type. We're just simply saving all the values and then flipping it across the axis. Real simple stuff, so don't worry that I'm not really talking too much about it. The inversion, this is less simple, but it's still the same thing as the previous one, where you take the determinant and then check if it's... Oh, I should have mentioned before, if the determinant is not equal to 0, it's actually, that's the only case when the matrix is invertible. If it is equal to 0, well, the matrix is not invertible at all, so you have to do this check. Be sure to add that if you're copying it by hand. That's very important. Oops. Now we're going to do negate. I'll copy and paste the determinant and the negation function here, so that we're pretty much finished with this. The negation function, very simple, and the determinant function is expanded for the 3x3 matrix here. And yeah, that would be our matrix 3x3. Let's make sure it compiles. Alright, we made an error at where's that? 97. Oops. Oh man. How did I? Okay. And at 111. Wow, okay. Yeah, forget I did that. That's a bit embarrassing, but yeah, that's fine. The last one we want to do is matrix 44, and this is going to be just a little bit different, so but not too much difference. Let's go ahead and copy over the include inclusion, and we're actually not using vector 2 anymore, to my knowledge yet. So yeah, for declared vector 3 and vector 4, here's the normal constructors. Now the difference in this is you notice you have a bigger area, and this is actually the W axis. And when we talk about more about 3D rendering in homogeneous coordinates, we're going to talk more about this W axis, but it's extremely valuable, and especially when it comes to 3D rendering. In fact, matrix 4 might really be the only matrix that matrix 44 might really be the only matrix that we actually use during this tutorial. So just keep that in mind. But we have the vector 2 and vector 3. Number 1 just to have it, and number 2 because they could be useful for physics applications if we ever start making a game engine out of this. Or if I ever wanted to switch this over to one of my C++ engines. Yeah, and also we have a scale and rotate function. The scale function, it's going to work by basically setting the... actually, I'll just show you when we make the implementation. But first, let's make our... First, let's add in this nice macro that we got here. And this will just be a faster way to do the determinant of a 3x3 matrix. I would not recommend copying this by hand because I probably didn't even show the entire thing. So definitely copy that one from GitHub. Alright, so I include the vector 3 and vector 4. Yeah, so you just pass in the values for a 3x3 matrix, and then it gives you the determinant. And the reason I did that was because I wanted to skip a function call. And I could probably put this into the defs.h and use it for the 3x3 matrix as well, but it doesn't really avoid the function call, so there's no reason to do it. But in our case, in the matrix 4x4, it will avoid a function call, so that's why we're doing it here. Now let's copy over the operator equals and assignment operators and stuff. Here is the function matrix 4x4, the initialization list, and then the copy constructor, real simple stuff, and then the operator equals. It's all correct, and then our virtual destructor. Now let's do the add subtract. There's that. Same as before. And now let's do the multiplication. This is the same as before once again, but this time it's going to be with a bigger matrix, which has been the pattern over and over for now. And now we'll do the transform. And there's that. And the identity matrix and the zero matrix, let's set that here. This is just the same thing. Go ahead and split these up by every 4. Oops. Okay. There we go. Okay, so we're setting the identity matrix to the zero matrix down here. Okay. Okay. The zero matrix is being set here. We'll do transpose, same as before, but this time with more numbers. And then inversion, again, exact same thing as before, but with more numbers. There's that, and now we have the negation. Then we'll do scale and rotate, and I'll talk a little bit more about these because we haven't seen them yet. Scale is going to be a nice function that will stretch the axes effectively, but it might not be exactly what you think. You'll notice that in order to scale the x-axis, we're actually multiplying everything on the top by the scale value in scale.x. Now you might think, why would we do that? Well, if you remember back to my definition of multiplying matrices, you're taking the dot product. So by multiplying all these values by the scale on the x-axis, you are effectively, when you multiply the matrix by the vector, you're effectively multiplying each x coordinate by the scale in this axis. And that's extremely cool. The reason why it makes sense is because think about it like this. If this is 1, 0, and 0, and 0, and this is 0, 1, and etc., just a normal identity matrix, when you multiply it, this x-axis is, this x component is the only one that multiplies with the other x component. So that doesn't return a 0 result, or a result of 0, because all these other values are 0. So by multiplying it there, you end up with it being scaled by the value in this corner. And obviously, if there are values in this area, it'll be scaled a little bit on x on the other columns as well. But yeah, that would have to do with things like skewing and rotation, and things we don't really want to go too much into. And same goes for the y-axis and the z-axis as well, so that all the scale will be stored within this little box of the matrix, which is very cool stuff. But that's how scale works. And this rotation stuff, I'm not going to be able to explain all the math behind it. But at one point I did know how it was derived. It's just not the kind of thing you want to remember, how this function was derived, the rotate function. I know it involved about 9 matrices, something like that. It involved a ton of matrices and a ton of identities. It was just not a fun thing to derive. I had to derive it on one of my exams, and since then I've never really thought about it. So yeah, just know this is just a simple derivation, not a simple one, but this was derived, and it's not something that I'd expect you to just know how to do randomly or intuitively, and I don't expect myself to know it either. So there's the rotate function. And how this would work is you give it a vector 3 axis and then an angle. So if this is 1, 0, 0 for the axis and then an angle of like 1.57, that'll be a 90 in radians. That'll be a 90-degree rotation on the x-axis. And there's a big problem with Euler angles, which we'll talk about in the next tutorial. It's something called gimbal lock. And I'll leave a link to a tutorial, or a link to a video explaining how that works and why gimbal lock is a problem. And that's actually the reason we're going to be using quaternions during this series, because gimbal lock can make some bad things happen. Although it probably won't be a big issue for us just making a simple render engine. We're still going to bake the quaternions just because they make things a lot easier when it comes to physics and making it so that objects can look at each other, and yeah, it's just a better way to represent rotations, so I don't see any reason to not do them. Although I guess they are a little bit harder to use, which is alright. So now let's do the determinant. With that in place, that should be everything for the matrix class. If we build cosine, yeah, we have to actually include math.h, because it uses sine and cosine in the rotate function, which is something I forgot. So I just wanted to make one small change to the matrix class, and it's something called translate. First of all, I'm in matrix 4x4 right now. And this is something I should have added, but it's actually the same idea as these functions. It's called translate, and we're going to take in a const vector 4 or vector 3 reference translation. So what this does is it's not to be confused with the trans function, because this means transform. This means translate, so don't confuse the two. The translate function will basically move the matrix. It'll translate the space of the matrix by a vector 3, and that only works because of homogeneous coordinates. But let's go ahead and paste that in here. Here's some of the code here. I have to modify it a bit because we're only taking in a const vector 3 reference and no need for a destination anymore. So the des is going to be, we just need to switch this to this, and then as far as the source goes, that's going to be this as well. Oh, and I do have to fix this. And then the vector is the same, and this would have to be switched to, once again, this. and then the same changes to that last column. And that's going to do it for our final changes. I'll see you all next time.